Hello everyone. Today we are here to discuss the pattern matching algorithm and some of its application in real life. This will be presented to you by Catherine Parmar and Shrijit Bhattacharya.
So what is pattern matching and why are we even discussing it? Well, pattern matching algorithm is one of those algorithms that we end up using in our daily lives without us even realizing it. So it is important today that we discuss what the algorithm really means and how over the years it has been developed to suit our needs as we are using it today. So you can see three pictures down below. So can you name what these are? On the left, extreme left, we have the DNA sequences, DNA sequencing. In the middle, we have a cipher wheel, and the right, we have someone trying to copy someone else's answers. All these three technologies have used pattern matching, and we we are going to see how pattern matching algorithm has developed over the years.
In the following section, we are going to discuss different versions of pattern matching algorithm developed over the years to ensure efficiency and easier working. We will explain why this approach was chosen, how it works with a given example, and its time complexity. So first we'll discuss naive algorithm, which uses brute force method. It is one of the simplest method among other pattern matching algorithm. It checks for all the character of the pattern in a given string. This algorithm is helpful for smaller text. In this slide, as you can see, we have a text string and a pattern string, and its output should be pattern found at index 0 and pattern found at index 9. We will further discuss how this naive algorithm works. As we can see, there is a text string and a pattern string. We'll take a window of size 4, which is the same size of pattern. Now, we'll run the window over the text string starting from index 0. We'll compare every character in the window with the pattern string. If it matches, we'll return the starting index as our output, otherwise we'll move forward with one character. Then we move the window forward and again compare. If it does not matches, we move forward until we reach the last window. We found another pattern at index 9, which we returned it as our output. Now we will discuss the time complexity of this algorithm. In best case scenario, the first character of pattern is not present at all in the text. So we move the window one by one over the text. We just need to compare the first character of current window to the first character of pattern. The time complexity in such case is big O of n. In worst case scenario, only the last character is different. In such cases, the time complexity will be m into n minus m plus 1, where n is the length of the text string, m is the length of the window size.
So I have pre-written down this string, and this is the pattern that I'm going to search within the string, right? So let me know if you can see it clearly. Okay. So as per pattern matching, I'll just go and compare this zeroth index of this string with the zeroth index of this pattern. So I compare A to A, it matches. I compare B to B, it matches. I compare C to C, it matches. And then I compare D to X, and it doesn't match. This is a mismatch. Okay. So our main point in the KMP algorithm is to not look at the string while not look back at the string. Whatever characters we have passed, we will try as much as possible to just overlook those characters when we are matching again. And I'll show you just how to do that. So you can see that ABC is the portion of the pattern that we found in the string as well. Now, the Knuth-Moritz-Part algorithm tells that we need to find a suffix that is equal to the prefix, or any such scenario where the suffix is equal to the prefix. But in ABC, C is not equal to A, so suffix not equal to prefix, and we can't really use their approach in this part of this pattern. So again, we go back. Again, we compare A to B. It's not a match. A to C is not a match. A to X is not a match. Then we again start comparing from this fourth index of the string. So we compare A to A, it matches. We compare B to B, it matches. We compare C to C, it matches. We compare D to D, it's a match. We compare A to A again, it's a match. We compare B to B, it's a match. But then we compare C to X and it's not a match. Now let's see the part of the pattern that we have covered in this second scenario. It's ABC, DAB. So now, as per the algorithm, we are going to observe whether in the part of the pattern that we have covered, is there any part of is there any suffix that is equal to the prefix, and we can see that AB equal to AB. Now, what this might seem quite non-relevant to you at this moment, but I'm going to explain to you why it is relevant. So AB equal to AB means that there is a portion in front of X where this prefix and suffix exist in the string as well, and this is this AB. Now, what Knuth-Morris-Pratt algorithm suggests is that we, in our next trial of trying to match the pattern with the string, we overlook this entire position and start from C to X. I'm going to explain you once more, just in case, that this pattern which was this prefix and suffix which was found in the pattern, this equals to this, and so the trial, while doing it the next time, does not take into account this one and starts directly from this third character C and to this X. Now we compare C to X. It's not a match, but we have successfully avoided comparing this to the pattern again, and this is where Knuth-Morris-Pratt algorithm starts to save time. So we compare C to X again, it's not a match, so it's gone. Then we again compare A to this A. So we compare A to A, B to B again, C to C, D to D, A to A, B to B, C to C, but now the Y is not equal to this D. So again, the backtracking, the Knuth-Morris-Pratt algorithm starts. The main gist of the algorithm. That is to compare in this entire position that we have covered, if there is any suffix equal to the prefix, any prefix equal to the suffix. So ABC equal to ABC. Here we can see ABC equal to ABC. Now, in this entire algorithm, I'm just switching sides to this end. So this ABC will be overlooked. The algorithm will not compare this ABC to that ABC again, because we know it's the same. Now we compare this D to this D, A to B, this C to C, and Y to Y. Now this is a match. The entire process is directed to stop backtracking process, and we are going to show you how this algorithm actually takes place in real life, and how the complexity is saved. This was just an initial example. I'm going to show you a real life example right now. Next, a pattern and how to find that pattern in the text without looking back at the text. First, we have to design a truth table. So a truth table, or as I call it, it's a table to find out the character length of the prefix and suffix. We have the pattern here A, B, C, A, B, Y, as you see up there. So these are the indexes 0, 1, 2, 3, 4 and 5. We have 2 pointers here, J and I. Whenever J equal to I, both J and I are incremented by 1, And if j is not equal to I, only I is incremented by 1, j stays at the position where it was. So first I compare j with I. A not equal to b, so 0, 0. I goes to plus 1. Is A equal to C? No, it's not. So it's 0 again. Now I plus 2, it goes to A. A equal to A, 1. Now both J and I move a place. I plus 3 and J now moves here. So is B equal to B? Yes, it is. So 2 right here. Now I moves one place more, J moves one place more. Is C equal to Y? No, it's not. So this is the truth table which I have with me. The length of the pattern is n, and the complexity of this truth table is O to On. Now we compare this pattern and see whether it exists in the text. We compare A with A, we compare B with B, and we compare C with X, which is a mismatch. So we will not look back at the pattern, we will straight look at this table. A, B, 0, nothing. No prefix, no suffix. So we need to start from the first letter again. Is A equal to A? Yes, it is. B equal to B? Yes, it is. C equal to C? A equal to A? B equal to B? Y equal to C? No. It's a mismatch. Now again, we don't look back at the text, we look back at this table. So A, B, C, A, B, Y. Where does it falter? At this B. What is the prefix at this place? 2. So we know a prefix of length 2 exists before the text where the mismatch happened. So we know that this part already exists, and we need to compare from this third character. So C equal to C, A equal to A, B equal to B, Y equal to Y. And we have the pattern in our text. So the length of the pattern is M, and the complexity of this is OM. So the entire complexity becomes OM plus N, and this is better than OMN, which was being achieved in naive or brute force algorithm. And here I conclude my Go-to-Merge algorithm. The third algorithm that was devised in this case is the Boyer-Moore algorithm, and we are going to discuss how the Boyer-Moore algorithm has its take on pattern matching in a string. So let's see a text and let's see a pattern. So this is our text string and the pattern is text. So any algorithm apart from the naive or the brute force approach attempts to how to skip the characters in the text where the pattern is to be searched. Because if a skip can take place logically, then the number of comparisons is reduced, and we can have a faster algorithm. So in Boyer-Moore algorithm, how it is different from any other algorithm is that in this algorithm, the pattern starts checking from the last character of the last character. While before this we were seeing everything was being checked from this end to this end. From left to the right. Now we'll be checking from the right to the left, and there are two heuristics with which we can do that. One, which I'm going to explain to you right now, is the bad character heuristic. So for the bad character heuristic is that, what do you mean by the you might question what do they mean by the bad character? Any character that causes a mismatch is called a bad character, and the people who developed this algorithm actually had to make a table so that the bad character can be got in a table, and we need not look back at the text to search for the pattern. So we will see what the bad character table looks like. So what's the pattern? It's TEST, text. Index. I'm just giving the indexes, no more. So this is the bad character table that I am going to construct. The function for this table is max of 1 comma length of the pattern, I am using LOP, length of pattern, minus index of character minus 1. So this is the function which I am going to use to compute this table. So first we look at T. Length of pattern is 4 in this case. Index of T is 0. So just doing the sum for 4 minus 1. So it's the maximum of 1 comma 3, which is 3. So we update this T as 3. What do you see for E? For E, we see that it's length of the pattern, that is 4 minus 1 minus 1. Maximum of 1 and 2 is 2. So for S, this is going to be 1. Now we face T again. So what happens in this case is that this T will be 4, this length of pattern, minus index of pattern 3 and minus 1. Now this is 0, but max of 1 comma 0 is 1. So this T will be 1. Now what happens in the math character table is that when one character occurs twice, the most recent value of T will be updated for this as well. So we will update this 3 to 1, and our table will translate to one, 2, 1, and this will be 4, length of pattern, because any character which is not present in the pattern will be taken as 4, and we'll see how it how it affects while we are computing the algorithm. So we have with us the pattern match table, that is TES, and we are going to see how we refer to this table to find this test in this text. So for test we start, I'm just going to rub it off. Start comparing from this character. Is T equal to S? No, T not equal to S. So what does S suggest? We shift by 1 right shift. So we shift to the right. This is a blank space. So any character which is not in the pattern is a blank space, and this compares to this star. It's a blank, it's A, it's a P, doesn't matter. It compares to this star because it's not in the pattern. So what does this suggest? Shift by 4. So we shift by 1, 2, 3, 4. Now we come to A. Does T compare to A? No, it doesn't. So we shift by 4 again, that is 1, 2, 3, 4. We compare to S. What does S suggest? We shift by 1. We again shift to here. Now T compares to T, S compares to S, E compares to E, T compares to T. So we see that there has been certain skips made in this entire text by referring to this table we have constructed below. And this is how the Boyer-Moore algorithm takes place. The complexity of this algorithm in the worst case is O to the power OOMN, which takes place when every character in the pattern is every character in the text, like A, and the best complexity that can be achieved is O M by N, where M is length of the text and N is text length of the pattern. And this is how we conclude the Boyer-Moore algorithm.
We'll now discuss Rabin-Karp algorithm. First of all, why do we even need this algorithm? Several string matching algorithm, including KMP algorithm and Boyer-Moore algorithm, reduces the worst case time for string matching by extracting more information from every mismatch, allowing them to skip over position of the text that are guaranteed not to be a match. The Rabin-Karp algorithm instead achieves its speedup by using a hash function to quickly perform an approximate check for each position. We will now discuss with an example how Rabin-Karp algorithm works. Now, we'll first calculate the hash value for pattern string. Let's assume it's x for now. We will now compare the hash value of the pattern with the hash value of the text. If they match, then character matching is performed. In this case, as we can see, it does not match, so we will move forward by one character. In step 2, the hash value matches with the hash value of the pattern. So now we will compare the character of both the strings. As the first character of both the string does not matches, we'll move forward. Now, as we move forward, we see that the hash value of text string and hash value of pattern string is the same. In the next step, we'll start comparing the characters of each string. As you can see in the step 6, we have found the pattern at position 3 in the text string. We'll return that position as our output. Now we'll discuss how we can count hash value for a pattern string or a text string. Let's say we have 10 letters as our input set. Each letter corresponds to a number. As mentioned in the slide, A corresponds to 1, B corresponds to 2, C corresponds to 3, and so on. To calculate the hash value, we need to use the formula given in the slide. Here, T is the number of characters in the input set, and M is the length of text string. V is the number each letter corresponds to. Here we have chosen a prime number in such a way that we can perform all the calculations with single precision arithmetic. Once we are done with comparing both the hash value, we calculate the hash value of the next window by subtracting the first term and adding the next term. Now we'll discuss the time complexity for this algorithm. Let's assume that the text length is n and the length of the pattern is m. In best case scenario, the time complexity will be big O of m plus n, because the hash step takes big O of n time, and once the algorithm finds a potential match, it verifies each letter to make sure that the match is true and not just a result of hashing collision. And therefore, it will check each of the m letter in the pattern. In worst case scenario, the time complexity is big O of m into n. This can happen if the prime number that we use for hashing is small, or there is always a hashing collision. For example, whenever the algorithm thinks it found a match, it verifies each of the m letters in the pattern. If there is collision at each step, m letter will be checked n times, resulting in a running time of big O of n into m. This can be avoided with a good choice of hash functions.
Now that we have seen how pattern matching algorithm has developed over the years and how different versions of the same algorithm has been developed by computer scientists to make it fast and efficient, we'll see a few use cases and daily life applications where pattern matching algorithm plays its role.
Now we'll see how pattern matching is used in DNA sequencing and image processing. In DNA sequencing, we have a huge sequence of proteins and RNA where we have to find a pattern inside the sequence. As we know, DNA strings are just a sequence of strings and a pattern is to be compared. If the pattern occurs within the sequence, then it is a match. And it is used in bioinformatics daily to make new discovery. It is used in pharmacy to make a new medicine. In image recognition, an image is nothing but a collection of pixels. These pixels are what our devices understand, and any facial recognition or AI-assisted picture recognition is a manifestation of pattern matching algorithm. A cluster of pixels are compared to each other, and these pictures are created by cluster of pixels.
I'm now going to show you how pattern matching is used in plagiarism detection and natural language processing. Both plagiarism detection and natural language processing use text-based pattern matching. In plagiarism detection, it is our job to see whether a certain collection of words or texts occur in a corpus or a dictionary. If the sequence of texts match the occurrence in the corpus exactly, we know that person B has copied from person A and this is a serious offense. In natural language processing and sentiment analysis, what happens is that certain corporations or individuals might hire computer scientists to check how their reviews are being affected and what kind of words are being used in their social media handles and blogs. A certain collection of words are made up, and these are compared against the entire social media history and the blogs to recover what kind of sentiment that they are projecting. While this is the scenario in the real world right now, improvements are being made on this domain, and over the years we might see different other applications of pattern matching algorithm as well.
Future scope of matching algorithm is to be combined with AI and machine learning to make further strides in the world of technology. We have placed three images from left to right. First is climate over a geographical region by comparing satellite images. Millions of images are being compared, and this empirical pattern matching shows how the climate over certain geographical region varies. Second is AI-assisted brain surgery. Our central nervous system is one of the most important part of our body. It consists of brain and spine. Over the years, medical fraternities have been trying to edge closer towards our technology-based diagnosis. Image of tumor and hemorrhages are studied and made sure while treating patients with AI-assisted brain surgery, a correct diagnosis will ensure less human error in surgical procedure. To make the machine understand the job in hand, images are transferred to it and the machine studies the pattern over the years in order to successfully deliver the job. This is a development over image processing.
The third picture we have is of a fingerprint. Don't you think our fingerprint are just patterns? When a fingerprint is taken for a certain person, we are just comparing the pattern on our fingerprint to a certain pattern that is stored in a machine. Pattern matching plays an important role in security processing as well, and we are just hopeful that over the years we can be more efficient while securing our systems and protect our data from breaches. So pattern matching plays an important role in cybersecurity as well.
Or
I would like to thank Coach Young for giving us the opportunity to study and present an exciting algorithm that practically helps running the world that we see today. So here is a picture of Professor Young with his favorite friend Srini, and we just hope that in the future we can also work on such wonderful algorithms and study them in depth.